Very good. As Bob said, what I'm going to do is talk about one of the methods that we've used, we've used this to contribute to some of the work that Bob and Laura McGuinn have been doing in terms of developing pollutant fields for North Carolina. We've also done it in Georgia. I'm not going to have time to talk too much about that. There's a lot of words up there, but basically what we've been doing is we have a method to fuse our chemical transport model. We use CMAQ with observations, and I'll talk a little bit about that. And we contributed previously to an effort being done as part of the CATHGEN studies, which you'll hear about later. But what we now are doing is extending it to a longer period into additional pollutants. And that's really what I'm going to focus on today, is look at this longer period, but primarily look at the additional pollutants, because it gives you an idea of some of the issues, but also some of the strengths of this approach. And the additional pollutants in particular are these trace metals that, at least in some studies, have been linked with various outcomes, probably because they're linked to a source. And I'll talk about that a little bit as well. And then we've been evaluating the results of this method as well as others. But so we'll talk about some of what are the specific things that I think are really issues going forward in terms of using some of these methods. So in particular, I'm going to talk about our applications to North Carolina. We've applied this at a coarser grid over all of the US. Our first studies were done actually in Georgia at a 4-kilometer scale. So we've done this at multiple scales. We've looked at urban versus regional areas. Today I'm going to focus on the North Carolina results. And one thing to note about North Carolina, as it shows there, is that you've got these various regions. You've got a coastal region, you've got some urban areas, you've got a mountain region. So you have very different characteristics in pollutant dynamics, different distribution of sources, et cetera, that can be potentially challenging to using some methods. You also have, as it shows here, different distributions of the intensity of the monitoring. Typically PM 2.5, we got lots of PM 2.5 monitors, but then you go to some of these gases, NO2, very few that you've got, and they're going to be concentrated in urban areas. And then ozone, a little bit more distributed, but ozone sort of, it's a nice regional pollutant anyway. And then you have these trace metals, which in some areas, they're not very well characterized at all. You may only have a couple of monitors with speciation, PM speciation in a state. You see South Carolina in particular, but in some areas you've got more sampling. So you've got these interesting issues, how they come together in terms of number of sites, sort of is it a regional pollutant versus a local pollutant, et cetera. And you can sort of look at this as sodium, as you might expect, is going to be primarily a coastal, high in the coastal areas from sea salt. So a number of different dynamics going on. One thing I will say is I'm going to talk a little bit about one of the performance evaluations. We use spatial clustering just to sort of be able to stress the approach a little bit more, and that shows you we used 10 clusters and this was PM 2.5. We did it for one other pollutant as well, where we had enough monitors, but I'll focus on PM 2.5. For things like sodium and these other metals and SO2, you just don't have enough monitors in our domain to do the spatial withholding. So when I talk about it, that's how we've grouped them. You can see different colors in terms of where the monitors were, sort of different urban areas, et cetera. So what we've done, again, is we've sort of fused CMAQ with interpolated results. And you can see the issue right here, everybody I think knows about it, is these air quality models can give you spatially and temporally detailed results. You can get it at an hourly scale, finer if you really wanted it. Whereas the interpolation, oops, wrong thing. Basically, you get a nice smooth field independent of what it is because it's driven only by where the sites are. So what we've done is we have this data fusion technique where we take CMAQ results and the observations and essentially put them together using two different types of formulas. And functionally what we're doing is, in one case, we're sort of fusing the CMAQ results to the observations at an annual scale, and in another case, we're doing it at a fine time scale, such that then we develop, we look at the correlations between the observations and observations between sites, as well as the observations to the CMAQ results. And based upon that, how well they correlate, we weight the two together. So there's our, essentially this shows you the flow. In the top one, we're essentially looking at longer term, if I can, I guess that's not working. You know, we have this annual average CMAQ that we then weight by the daily observations versus the annual average observations. And in the other case, we do it exactly opposite. Then we blend the two based upon how well they're correlated with the individual monitors. So you come up with this blend between the two. So that is the basic technique. One thing I should note is that we use a nonlinear, even though it shows a linear relationship between them, it's actually nonlinear. That's important because, as it turns out, air quality models, particularly for primary pollutants, have a nonlinear sort of relationship, primarily because of how well you capture the meteorology. So that's one of the things that sort of separates this from some of the other techniques. So here's what you get, is you start with the CMAQ, you have the interpolation, and you end with a data fusion approach that captures the spatial and temporal information better. So in our initial work, we applied it for North Carolina for 2006 to 2008, and we compared it to some other methods. Just quickly, and one of them was two-stage statistical model. This is Howard Chang's work at Emory. We compared it to observations, we compared it to straight interpolation, and also to data fusion. And you can see one of the differences is in the data fusion technique. You have multiple species. We use CMAQ at 12 kilometers. And just to give you an idea of the results, I'm not going to, since this was work completed a year or so ago, not go into the details, but the data fusion technique, if you without withholding, you get a 0.95. But when you start really doing it, we use 10% random withholding as well as spatially grouping withholding. And this is for PM2.5, you get R-squares of 0.82 and 0.73. And in a place like North Carolina, you definitely have these different groups. We had sort of a set of urban groups, a coastal group, and a mountain group. And that really is what drives it down, but I think it's the appropriate way to do it. So one thing I'd say is, in some ways, I look at many of these approaches that really blend observations with satellite models, chemical transport models, multiple together. They work well. And so with that, so just in terms of the prior work, you're going to hear more about how this was some of our work, and this showed up in a paper by one of my students, Wong et al., and it's being used by Laura McGuinn. So in the new work, we applied it to a longer period and added additional species. And this really gets into some of the issues. First, if you look at the PM2.5 over time, what this slide is here to show is that if you just use CMAQ, there's a significant bias. One thing no one should ever use chemical transport models without correcting, because you have these large biases. But what you do see is it sort of does pick up the annual variations. Not perfectly, but it does pick them up. And so that was PM2.5. Ozone, the same thing, except the ozone is biased way high. This is very typical of chemical transport models. But when you do the data fusion, you get the bias comes down. One thing it does do is it reduces the variability somewhat. Again, that's something inherent to the chemical transport models. Okay, so here comes sort of, I know this is a deadly table, and sorry about this. Actually, it doesn't have some of the things, I must not have put my latest version on. But what I want this to show, and hopefully you can pull it out, is that the first half of it, where you see all these red, or sort of a red, pink, purple shading to it, those are sort of the the species we did first time around, sort of your typical species that are often used. The first row is PM 2.5 mass, second row is elemental carbon, et cetera, going down to SO2. And the ones that are highlighted in purple, if you will, have R squareds above 0.5. So the model performed reasonably well. It tends to perform similarly year to year, though sometimes you get some really bad years and sometimes you get some good years. But you can look at the all years together and see what it shows. The next set, almost none of those are highlighted in red, are the new trace metals. And there's real reasons why the models don't perform as well for those. They're spatially much more variable, there's fewer sites, and they're more source specific. Now, when we use this data fusion technique, you see that you get significant increases in the R squareds for both. And you actually get reasonable R squareds for some of these trace metals that performed rather poorly before. Now, none of this is yet using data withholding, so we'll see what that does. We haven't had a chance to do that. But the other thing to take away from it is you still have these bad actors, if you will, copper and lead, and they've improved. The performance obviously has improved, just not as much as the other ones. So we can look not only at the correlations, but look at the biases. You get sort of a similar thing, is that for many of these trace metals, you get significant and typically positive biases in the simulated concentrations. And sometimes you get, so that CMAQ minus observed is what it shows. And when you do the data fusion, the bias typically goes away. You still see things like a zinc, whatever, that actually increase the bias. And we're looking into that. When you start looking at the air, so this is the normalized root mean square air, sort of a similar picture is that for the traditional pollutants that we've used before, it stays, that the errors weren't quite so high, and when you apply the data fusion, they go down significantly. And for the metals, they sort of are similar, but they start much larger and then they go down. But you still have a couple of bad actors as well. So just as a conclusion, again, this says in some ways too much. Just a few highlights. The air quality models allow you to developing these spatial fields for trace metals and gases. And we can do it producing relatively unbiased low error fields. But the thing I'd really take away from this is that multiple methods actually do work quite well, I think, linking them together. The main thing I like about using chemical transport models with this fusing technique is that you can get results for species that typically you can't, that are going to be hard elsewise, and you can get quantitative source-specific impacts. Thank you very much.
Thank you, Ted. Again, we're running a little behind time, but we have time for one burning question, and one burning question only if someone has one.